Okay, so we are starting recording and let's start the class. So welcome back. I hope you had a good break and yeah, I should stop viewing the chats. Otherwise, it might distract me. So let me stop that. And yeah, so we had a good break. uh, So let's come back and it's a new start. We are going to start nth order linear differential equations today, and you should find it relatively easy if you have followed second order theory very well. We will see. So let me start sharing the screen. One of you could confirm as usual.
Yes, sir, we can see.
Okay. So today we are starting higher order, which means nth order linear differential equations where n is any natural number. Okay. Up to now we have done n equal to 2. N equal to 1 was very easy. See, this is not about Picard. This is linear. So n equal to 1 was very, very easy. N equal to 2 was not so easy, but we have some familiarity via many lectures. And now we are going to do step up and do general n. But as you will see, general and computationally, you may have a bit more to do, but the theory is exactly the same as n equal to 2. So it is quite easy if you have followed n equal to 2 very well. Okay. So yeah, so I have put this here also. Hope you had a good break. And corona cases are also coming down throughout the country. And you had a good exam as you told me. So that's always good before a break. And let's see, hopefully. So I think half the course is over. Today is lecture 10. And I guess there may be 20, 21 lectures maximum, maybe less because we skipped 2 classes. So I think half the course is over. So it's going well, I hope. It's certainly going well for me. And I hope for you also. And so, yeah, this is one announcement. I'm not feeling fully well. And also, because Tuesday we did not have a class. If I take the interactive session, there will be some asymmetry between D1 and D2. That is one reason. And also, I'm not feeling all that well. So we will cancel today's interactive session. Okay, so please don't come at 3:30 today. So we will meet on Monday as usual. And this I already told you verbally. If you have followed the second order theory well, you will find the next several lectures. Today we are starting nth order, and the next several lectures will be should be quite easy for you. So let's start. So an nth order linear differential equation will be of this form, where as you can see, all the derivatives are coming linearly, and there are these coefficients and gx on the right side, and these coefficients can be as complicated as you want. We put no condition. Okay, but of course we are going to assume that they are continuous throughout your interval in order to get good theorems. Okay, soon that we will put, but in general we don't have to put that, but we usually put. Okay, so if we don't say anything, it is assumed that it is continuous. That has been the practice throughout, and that will be the practice now also. So assume that the functions are continuous. So many times, we won't mention this because always this is a standing condition. So if I forget to mention, it is understood. Okay, assume that these are all continuous on an interval I, and assume further that the leading coefficient, the coefficient of the highest derivative, is never vanishing on I. What can you do if that is the case? What will you do naturally? If this function is never zero on your interval of definition, what will you do?
Divide by
Divide by
divide the
Divide by that, and then what do you call such an equation?
standard form.
Standard form.
Standard form. Correct. So very good. So if the leading coefficient is never zero, you may call that equation non-singular, and then we can put this into standard form. So this is crucial for most of our results, as you will recall from second order. So in nth order, it's exact same story, very similar story. Put it into standard form. Do you agree that these coefficients are also continuous? All these coefficients are continuous?
yes.
Yes,
Yes.
Yes.
because all these are continuous, and continuous by continuous is continuous, provided denominator is never zero. That's your assumption. So all these coefficients are continuous. When will you call this equation homogeneous?
Rx is
R,
zero.
Rx is 0.
So theory is exactly the same. So you know everything you know. Yeah, if Rx is identically 0, you will call it homogeneous. And how did you solve a second order non-homogeneous equation?
Found a standard solution and then added a linear combination of the basis of the homogeneous solution.
So we will do exactly the same now. We will do exactly the same. So let's recall our systematic study of second order linear differential equations will guide us in our study of nth order linear equations. So quick recall. So in the next 5 or 6 or 7 lines, bullet points, I am recalling whatever we have done till now. Okay. So the first thing that we did is appeal to 106, use dimension basis, etc. And we converted a second order standard form thing as a linear operator. What was C2I? What was C2I?
Vector space of all the functions which have a continuous derivative.
Yeah. So continuous second derivative.
F dash and F double dash all are
Yeah, all
continuous.
of them are continuous. So what will be our generalization today? Instead of this space, what will be the space that we consider?
Cn
Cn.
of
I.
Cn of
Ni, and what should be the definition?
F dash dot F n times all continuous.
All exist and all are continuous. And will we change the right hand side?
No.
No,
No.
it will be the same CI. It will be the same CI and I will still call it by L. So the first slide is, first point is done. You know what we are going to do. Second thing was we had a dimension theorem about the dimension of kernel L. Okay, what was the condition on L? L consisted of a second order differential operator in standard form whose coefficients were continuous. These were the assumptions. And then what was the dimension theorem? Dimension of kernel L is, first of all, kernel will form a vector space. L is a linear operator and therefore kernel will be a vector space. And the dimension theorem told you that the dimension is
N.
is
N.
no, in that I'm recalling 2. And
2.
therefore today what will be the dimension theorem? Dimension is
N.
N. Okay, exactly same story. And then we had existence and uniqueness for IVPs. IVP is initial value problem. How did an IVP look like in second order? You had a second order equation y double prime plus pxy prime plus qxy equal to 0. And what was the initial value?
Y of x naught is given and y dash of x naught is.
Yes. So how will an IVP look like now?
Y of x naught, y dash, and so on till y.
So you will have
nth.
an nth order, absolutely. So you have an nth order linear equation and you will have one constraint point x naught and then y at x naught will be given some value. Y prime at x naught will be given up to y, which derivative?
N minus 1.
Minus first derivative. So all these will be given. That will be IVP. And we had to assume continuity of coefficients and get existence and uniqueness. This is very, very, this is the beauty of this result. Wherever you assume continuity, exactly there you are going to get existence and uniqueness. So this is why linear theory is good. Non-linear, we did not have this, right? Even in first order non-linear Picard, you could guarantee only on a subinterval, but linear, it is exactly the same interval where continuity is given. And if life is good, if world is good, will you have an existence uniqueness theorem for IVPs for nth order equations? Assume life is good. So what is your answer? Will we have an existence?
Yes.
Yes. What will be the condition? Condition is in standard form and continuity is assumed throughout the interval. And where are you going to get existence uniqueness in the nth order case? What is your guess? I told you it is same as the second order story.
Exact same interval.
Exact same interval. Okay, so remember on the same I, you are going to get existence and uniqueness in nth order also. And did we prove this result in second order?
No.
We skip the proof. Do you think we will prove the result in nth order? No. Because second order itself, I said we will skip. So of course we will skip the proof. But did we prove this result in second order?
Yes.
Yes. Not when I stated it. Not when I stated it, but later. After existence uniqueness, assuming existence uniqueness, I proved dimension theorem. Do you think we will prove it in nth order?
Perhaps.
Yes. So after assuming this, we will come back and prove this. Proof will be exactly similar. Okay, so we can give a proof. It will be a bit quick because anyway, we are not going to ask you to prove something. But those of you who are interested should know the proof. So very quickly, we will do that. It's the same story. If you understood the second order proof, you will understand the nth order proof. Then we did in one lecture, completely we devoted to linear dependence and independence in terms of Wronskian. And can one of you quickly tell me what was the definition of Wronskian?
Determinant of the solution of functions
F,
from the
G and
first
F prime, G prime. Will you have a Wronskian in the nth case?
Yes.
Yes, sir.
What kind of, what will be the matrix size?
N by
N cross
N
N.
cross N.
What will be the first row?
All the
F,
All
all
the
the
F.
functions.
all the functions.
F1, F2, etc. Fn. What will be the second row?
First
F
derivative.
prime
First
log.
derivative.
First derivatives.
And the last row will be?
Nth
N
derivative.
minus
N,
one.
N minus one is derivative.
N
And
minus
we
one
had this.
derivative.
And how did we do dependence independence? We had one-way result that if two functions are dependent, then Wronskian is always zero. That had nothing to do with differential equations. That is still true. That is still true. The same proof works. And for independence, we assumed if you have two solutions of a second order linear differential equation, continuous coefficients in standard form, then they are, then we proved Abel's identity. And then we claim that if it is zero at some point, then it is zero everywhere. And then we concluded that linear dependent if and only if Wronskian is zero somewhere, right? If Wronskian is non-zero at any point, then these solutions are independent. We will have exactly the same result in nth order. We will prove all these things today. Okay. Then we wrote down the general solution in the constant coefficient case, right? How did we do this? We had to analyze three cases: equal real roots, distinct real roots, and complex roots. And similarly, we can do in nth order constant. What happened? Do you see anything?
Yes,
Yes,
sir.
sir.
What do you see? Can you see the slides?
Yes,
sir.
sir.
Okay, so on my screen, something else happened. 1 second. Some Adobe something came. You can still see the slides, right?
Yes, sir.
Okay, very good. So constant coefficient case also we can do. If time is there, I will start the constant coefficient case. You will be able to guess. So, I would also like you to start guessing the answers. And once you can make a good guess, you can try to prove it. Okay. And Cauchy-Euler also we did. And we can do Cauchy-Euler for nth order also. Same guess, same strategy. And then non-homogeneous case, as you said, you had to do one particular solution, and then together with the general solution of the homogeneous case, you can do the general solution of the non-homogeneous case. We had two methods to do one particular solution. One was called undetermined coefficients, and the other is called variation of parameters. Both these will work in nth order also. So we will do that. Not today, in the next class. Okay. So both these will work. So basically, this is what we have done till now, right? So I said we may have 5 or 6 or 7 bullet points. How many points are there? 1, 2, 3, 4, 5, 6. Okay. So we had 6 bullet points, quickly recalling whatever we have done till now. And all these will go through in nth order. Okay, so let's start. So CNI, you have already told me all functions defined on I, real valued functions. Up to nth order, all derivatives exist. Not only that, we are assuming that all of them are continuous. This is a vector space under usual addition and scalar multiplication. And we define this linear operator by, if your equation is yn plus p1x yn minus 1 plus pnx y, then you define the linear operator L of f by like this, exactly using the coefficients of your differential equation. And this L is clearly a linear transformation, and this answer is continuous because you are assuming all these derivatives are continuous and these coefficients are continuous, product of continuous is continuous, sum of continuous is continuous. Therefore, this is continuous. Okay. So L is a linear transformation. Sometimes we will use this notation. D is the differential operator. What is D? D is the operator. D is d by dx. So what is d square? D square by dx square. So d is the operator. Dk is, okay, so there's a typo here, no? My notation is d upper k. Okay. So if I don't correct it, someone could remind me by an email. This k should be up. Let me see the next slides. Either it should be uniformly down or it should be uniformly up. I think up is a better notation. And L is a linear differential operator. Okay, L is called a linear differential operator. And kernel L is a subspace of the left-hand side, the domain, and it consists precisely of solutions of the homogeneous differential equations. Right? This is your operator, and kernel is those y such that L of y is 0, which is exactly this. So solutions of the homogeneous differential equation, they form a vector space. So kernel of L, it is either the null space of L, or we may say the solution space of this differential equation. And the dimension theorem is dimension of kernel of L is n. And if we assume the existence uniqueness theorem, we can give a proof for this. So what are the conditions here which I am not saying? This L is in standard form, and having put it in standard form, the coefficients are continuous. Right? As in the quiz, you have seen that the dimension theorem is not true if, when you put it in standard form, if coefficients are not continuous. Yeah, is there a question? Is there a question? Okay. Otherwise, please mute. If there's no question, please mute. So this, this I haven't stated all the conditions. What are the conditions here? Having put it in standard form, all the coefficients are continuous. Having put it in standard form, very, very important. So the dimension is n. N is the order. And IVP in this context, already you have recalled. So this is one advantage if I make you recall even before I come to that, because I can go faster. It is an equation like this. There is one constraint point x naught. It's the same x naught everywhere in bracket. And y at x naught is some number k naught, some real value, some real number. Y1 at x naught is some other real number. It could be the same also, but in general, some other real number. And n minus first derivative evaluated at x naught as some other real number. And with x naught from your interval I, where all the coefficients are continuous. And this is the existence uniqueness theorem. If all the coefficients are continuous throughout the interval I containing x naught, then the IVP has a unique solution. There is a solution. Moreover, the solution is unique. Very, very important on I, throughout I, not a subinterval. Throughout I, you know that. Okay. So once again, let me stress this. Note that both existence and uniqueness are guaranteed on the same I, This is the beauty of linear theory, where continuity of the coefficients is given. Okay. This is not the case in nonlinear theory. It is true in linear theory. This is not the case in nonlinear theory. The only time we did nonlinear equation is first order, Picard, etc. There itself, this is not true. Not on the same I, but linear, it's true. And this is a difficult theorem which we will not prove. We will skip the proof. So once again, I am recalling you had CNI, you had the linear transformation L defined like this, and we had this other notation, and we said kernel of L has, do you see a typo here? it may not be there on Moodle, but right now there is a small typo here. Can you see that? I mean, there's a fun question just to see how observant you are. You can see on the screen. Can you see on the screen page number coming? So page 44 you can see, page 45 you can see, and now see page 46, but nothing happened. Do you know what this typo is?
D sub K.
No, okay, that is fine. That is a repeated typo. This typo already came. So by copy paste, that typo came. I'm asking about another typo, which is not there on the PDF file. It is somewhere else. Do you see that?
The P function should be acting on X.
Say that again.
The PI functions should be acting on X, not on the
Well,
function.
that you need not specify. That is understood. That is not a typo. I'm not talking about a typo which you can see on the PDF.
An extra pause in the later.
Yeah, an extra pause. There's a typo in my text slide, as you can see here. See, when I move, it said page 44, then page 45, the new thing came, then page 46 is coming, but there's nothing. So there's a typo in my text, which you will not see on Moodle because Moodle is without pauses. Okay. So I'm just repeating this many times so that I remember later that there is one more typo for me to correct. So there are 3 typos. Subscript K versus superscript K on 2 slides and 1 extra pause. Okay, so the question is, can you give an explicit basis of kernel of L? Do you remember the strategy in dimension 2 in second order? How did we get a basis? There was a theorem, no? Can one of you recall the theorem? How did we get an explicit basis?
If it's not a
Yeah, go ahead.
independent.
Yes. So what you're saying is, if there is a point x0, it's up to you. Suppose you can choose a point x0 such that f of x0, f prime x0, that is a vector in R2, and g of x0, g prime x0. F and G are solutions of your second order ODE. And if f x0, f prime x0, that pair, and g x0, g prime x0, that pair, if these two are, what is the keyword? If these two are independent as vectors in R2, then we showed that f and g are linearly independent. And they will automatically be, then we showed that f and g are linearly independent as just linear algebra. We showed that f and g will span. F and g will span. Okay. Can one of you recall, since for quiz you would have revised, so you might remember the proof. Can one of you recall the main idea of the proof?
Assumed h of x such that h of x0 is equals to c f of x0 plus d g of x0 as well as.
Yes. Yeah. One more person can go ahead. Yeah, you try to.
We tried to we tried to span this function f of f and g.
Yeah.
We tried to find the coefficients such that it spans the whole function space.
Yes.
Whole solution space.
And what is given to you is a linear algebra result that these two vectors are independent. So if h were to be a span of f and g, in particular h of x0 will be a span of f x0 g x0, and h prime x0 will be a span of f prime x0 g prime x0. Now can you get c and d? Can you solve for c and d so that at x0 these equations are satisfied?
Yes.
The equations are hx0 equal to cfx0 plus dgx0, and h prime x0 equal to c f prime x0 plus d g prime x0. Can you solve for c and d?
Yes, sir.
Yes. Because that is what is given to you. fx0, f prime x0, and g prime gx0, g prime x0, they are linearly independent. So if you form that Wronskian matrix, that is invertible. That means you can solve for that. Now there was a key observation. After this, how do you, from one point, how did you get to the full function? There's one word that you have to tell me, and then I will know that you understand.
Unique solution.
Unique solution.
Existence uniqueness you apply to which function?
H of x.
H of x minus f of x minus t
minus
g of
h minus cf minus dg. H minus cf minus dg, and identically 0. Okay, so same strategy will work. So recall the theorem we had. I'm repeating whatever we discussed. In fact, what you told me, if f and g are two solutions with continuous coefficients, and if these two are linearly independent for some x0 is up to you. You can choose an x0. Okay, then the solution space is a linear span of f and g. If H is, and I'm recalling the proof, if H is a solution, then we can solve for CD such that Hx0 is this, H prime x0 is this. This you can write as a matrix, and the determinant of the matrix is non-zero is given. And therefore you can solve for C and D. You can use Cramer's rule, whatever. You can solve for this and apply uniqueness theorem finally to which function? You can apply it to the function y1 equal to h minus cf minus dg, and y2 is identically 0. What is IVP here? IVP is the given differential equation together with what are the conditions, initial conditions?
Y of x0 is 0 and y dash of x0 is 0.
Y at x0 is 0 and y prime at x0 is 0. So trivial solution automatically satisfies that, and H, F and G, all those satisfy. Therefore, this also, all those satisfy these equations. So H minus CF minus DG at x0 is 0 from this, and H prime minus CF prime minus DG prime is also 0 at x0 from this. Therefore, both these will satisfy, and it follows from the existence uniqueness theorem. We can do the same thing, no? Is there anything which is specific to 2 here? Can't we do this for n? How will you do this for n? Okay, somebody, can you do it for 3? Instead of 2, can you do it for 3? What will be the proof for 3? What should be your hypothesis?
We can write the three initial conditions as a linear combination of.
Yeah, but let us start slowly.
Second derivative.
Instead of this line, what I am highlighting, if you want a theorem for 3, n equal to 3, what should be your hypothesis?
F of x naught, f dash of x naught, g of x naught, g dash of x naught, and h of x naught, h dash of x naught.
Yes. So
and h
double
dash.
You are absolutely right. So instead of f and g are two solutions, what should be your starting?
F, G, H.
F, G, H are instead of three solutions. And if you come here, instead of this, what should be your condition? There is some x naught such that f x naught, f prime x naught, comma, f double dash x naught, g x naught, g double dash, g prime x naught, comma, g double dash x naught, and one more vector, h x naught, h dash x naught, h double dash x naught. What is the hypothesis? These three are linearly independent in R3. For some x naught, then the claim is the solution space is the linear span of f, g, and h. How will you prove it? If there is another, so you should call it something else. Can you give me one letter other than f, g, and h? Let us say if
E.
U.
E.
E is not a function, no? E is never a function.
U.
M.
Okay, U. Let us take U. If U is another solution, you can find, maybe here you can take E, C, D, and E, such that U is CF plus DG plus EH at x naught, and therefore you will get H prime, and for U prime and U double prime, and Wronskian is non-zero. Why? Wronskian of FGH at x naught is non-zero because of this condition. These three are linearly independent. And then you will apply the unique existence uniqueness theorem to which function? U minus CF minus DG minus EH, and Y2 identically 0. So that's how you will do it. So let's do the proof. This will be the Wronskian that you consider. And if Y1, etc., Yn are solutions, and if the Wronskian is non-zero is given to you, then any solution can be written as a linear combination of Y1, etc., Yn. And how will you prove it? Let Y be any solution, and you are going to solve for unique C1, etc., Cn. This was your CDE. Now that there are n things, I will change my notation. Instead of CDEF, I will write C1, etc., Cn, such that you will get this equation. This is exactly the equation that you earlier had, right? You have this Wronskian matrix, and you have this coefficients, and you have y x naught, etc. This, and you can solve for C1, C2, etc. Cn. Why? You can solve for this because
Matrix is invertible.
matrix is invertible. That is what is given to you. So what is given to you is there are n vectors in Rn which are linearly independent. And that exactly means this matrix is invertible. Therefore, this system of linear equations you can solve. And you would have got C1, C2, etc. Cn. So where are you right now? You know n solutions y1, etc. yn. And you know one more solution y, an arbitrary solution. So you know that the functions y and y1, etc. yn. And you have solved for C1, etc. Cn. And now what are the two functions that you will consider in order to apply the uniqueness theorem? One is identically equal to 0 function, and the other is, one of you tell me?
Y minus C1, Y1 minus C2, Y2.
Absolutely.
Minus up to Cn.
Yes, y minus C1, Y1 minus Cn, Yn. So you apply uniqueness theorem to y minus C1, Y1 minus ... minus Cn, Yn and identically 0. Both are solutions of which IVP? The given differential equations together with what are the initial conditions?
Y equal to 0, y dash equal to 0, and so on.
Where? It is an IVP. What is your constraint point?
Of x naught.
Yeah, y at x naught is 0, y at x naught is 0, y prime at x naught is 0, etc. And minus first derivative at x naught is 0. If you consider the given differential equation together with this IVP, all these initial values, then identically 0 satisfies that, and this function satisfies that. This function satisfies that is exactly this matrix system that is given to you. And therefore, by the uniqueness result, you will get this equal to 0, which means y is a linear combination of y1, etc. yn, which is what you wanted to prove. And from the given condition, it is easy. It's easy linear algebra to prove that these functions are anyway linearly independent. So you would have got a basis. You would have got an explicit basis. So, and now we will come to Wronskian and linear independence. So this also we have done earlier. We have seen that the Wronskian of any two solutions, f and g, is given by, what was the word for this? One word you have to give me. What is the word?
Able.
Able. Okay. So what was the main point here? Main point here is the Wronskian in general depends on Wronskian at any one point and only on the coefficient of y prime. It does not depend on qx. Do you think there is a generalization of Abel's identity to nth order? Yes or no?
Yes.
Yes. And what would be the shape of Abel's identity? Do you think that the Wronskian at any point will be Wronskian at one point and e power some integral? If that is true, let me tell you that that is true, then integral will depend on which coefficient? First being the coefficient of
y power n minus 1.
n minus 1 and nothing else, when it is a homogeneous equation. Okay, and nothing else. This is true. This was your guess, so very good. This is how mathematics progresses, not just mathematics. Whatever branch you are in, any engineering branch, whatever you do, you have to develop some intuition. Intuition comes from familiarity. Because we have done second order in detail over many lectures, you have some first guess. Your first guess could be wrong. My throat is hurting me when I'm getting excited, but anyway, your first guess could be wrong. That's okay. In this case, it happened to be right. So if your first guess is wrong, you will have a natural second guess. Okay, that's how your intuition helps you in order to formulate the correct results. It is another matter if you are in mathematics that you have to give a rigorous proof later. Your guess, you cannot sit relaxedly based on your guess. You have to give it a proof. Okay, but that's in mathematics. If you are in engineering or physics, many times getting the right result also may be good enough. And that comes from your physical intuition, your mathematical intuition. Okay. So your guess is correct here, and we are going to prove this. And as I said, nth order, the only complication is computation takes a bit more time, because after all, if you have three functions, when you take derivative, you have to take derivative 3 times, etc. Except for that, that's not real difficulty, right? That is only computational difficulty. That's not conceptual difficulty. Conceptually, there is nothing more here. This is something that we have done in second order, and that's what we are going to do now. So we did notice that the answer depends only on Px and not on Qx. And what should be the nth order analog? Nth order analog is if y1, y2, etc., yn are solutions of second order homogeneous in standard form, we will also assume PIs are continuous. Maybe there's a slightly better result. Let's not bother. PIs are continuous. Then Abel's identity tells you that the Wronskian at any point is, can you fill up what is going to come here? W at
A times
y1, y2, etc. yn, my comma, y1, comma, y2, comma, yn. My notation is semicolon. Instead of x a times e power
minus integral a to x p of t.
P1 dt.
P1
t dt. Okay, so that is exactly the result. You have guessed the result. y1, y2 Wronskian at one point e power. It is exactly that point in the lower integral. This is by evaluating the constant in your first order differential equation minus P1 t dt. Do you remember the proof of this? Then we can do the proof of, we will prove the nth order thing. If you can recall the proof of this, then we can prove this also. What is the main idea?
We found W dash.
Yes, we found W dash and you got a nice separable differential equation. Do you remember the differential equation? W prime equal to
minus
P
minus P times
W.
So here also you will get the same differential equation, W prime equal to minus P1 times W. That's enough, no? In order to get this, by integrating, you can get this. So we have to find a differential equation of the form W prime equal to minus P1 times W. And if you recall, what did we do here? You wrote down W prime and W involved Fg prime minus F prime G, and W prime involved Fg double prime minus F double prime G. And then what did you do? You substituted what?
F double prime value.
F double prime and G double prime you substituted from the differential equation, and then you rearrange terms, and some terms became zero because F double prime, F and G are solutions of differential equation. And the rearranged things, when you wrote back, you got minus P times F, minus P times the Wronskian. Exactly the same strategy will work. So once again, our earlier proof will go through, but because there are n things, I will write it a bit more systematically. We have to claim that W prime equal to minus P1 times W. We make the same claim here. W prime is minus P1 times W. And notice, I'm going to rewrite our proof slightly differently. Instead of y1, y2 prime minus y1 prime, y2, let me use the determinant notation. And y1, y2 prime minus y1 prime, y2, what was the Wronskian? What was the derivative of this?
Y1, Y2, Y1 double dash, Y2, Y2 double.
Yes, but two more terms came. No, there were 4 terms. 2 terms got cancelled.
Yes. Y1.
Yes. So if you remember the 4 terms, it is same as writing one term is this and the other term is this. Do you agree?
Yes, sir.
One term is this. So this has 2 terms and this has 2 terms. And this became 0. This got cancelled. The first one got cancelled because it's the same row or same column. So this became cancelled and this became the answer. Is this suggestive of what will happen? Now you think of the n by n Wronskian and we have to take its first derivative. Can you guess what will be the first derivative? If you have 3 by 3 Wronskian.
Only the last column.
First 2 rows will be same.
Only the last determinant would be surviving.
Yeah, but will it be so if it is 3 by 3, it will be a sum of how many determinants?
3.
3 determinants.
3.
Out of which 2 are zero.
Okay, 3 determinants. And the first 2 will be 0 because there will be repetition of rows or columns. Okay, and the last one will remain. Okay, so that is the idea. So this is this. And in this, we substituted for y1 double prime, rearrange the terms. That's how we got it. So we do the same thing. The derivative of this is the sum of n determinants. You agree, right? I'm going to do it in plain English, the proof. Okay, because otherwise, n by n determinant, when I write, size will be too much. So I'm going to do it in plain English. This is what we observed. It will be the sum of n determinants. And as you told me, with derivative being taken in the first row in the first one, can you tell me in the second determinant where will be the derivative?
Second.
In the second row, in the second row, in the second one, etc. Okay. And therefore, except in the last one, what will happen? There will be repetition of rows, and therefore, except the last one, all will vanish because two rows are identical. And therefore, in the last one, only the last one will remain. In the last one, you will make the substitution. So in the last one, when you make the substitution, you have, visualize this determinant. So if you come back to 2 by 2, you get this determinant and you are making the substitution minus p1x y1 prime minus p2x y1 and minus p1x y2 prime minus p2x y2. That 2 by 2 determinant is again sum of two determinants, right? You agree? It is of the form ay1 prime plus a2y. So can't you write it as sum of a1 p1 y1 and a2 p2 y2 and another determinant with p2 y1 and p2 y2? You agree with that? If you have ax plus b, if you have a y1 prime plus b y1, in the first determinant it will be a y1 prime, and in the second it will be b y1. Do you agree?
Yes.
A determinant can be written in one determinant. If you have a plus c coming, then you can write it as determinant with a there and determinant with c there, right? Throughout one row, you have to make this. So doing that in the last row, so you got n determinants. You got n determinants here. First n minus 1 was 0. Only the last one remained. In the last one, in the last row, you make the substitution. Do you agree that this determinant can be written as sum of n determinants?
Yes.
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 Okay. And in which also there will be cancellations, no?
Yes.
Yes, there will be cancellations because this will be sum of n determinants, and once again all but one will vanish. Why is that? Because this term will not vanish. This determinant will not vanish, but this etc. will vanish. Why is that?
Because all
y
are
Rows are repeating.
y power n minus 2 is there. Rows are not repeating, but two rows are
Multiples of
Proportional.
proportional because it is a p2 times the second row. P2 times the n minus second row will be the last row. Here, Pn times the first row will be the last row. So rows are proportional. So all these things will vanish. So only one determinant will remain. And you look what is the determinant. Minus P1 is common. So minus P1, if you take out, what is that remaining determinant?
W.
Wronskian.
Is exactly the Wronskian. So you have proved it. So non-vanishing one gives you minus P1 times the Wronskian. Do you agree? So once you understand the concepts, writing down the proofs can be plain English, as I have done here. It's all plain English. There is nothing more to do. So mathematics proof can be conceptual and can be plain English. We can talk. I don't need the slides. In fact, I did not even need this slide. If you were really visualizing the whole argument, we could have done it. This is how, good chess players play chess also, I am told. I don't know chess that well. So for me to play chess, I need, your 8x8 chess board. And I have to see the pawn and the king and the queen and the rook and everything. But very good chess players, how they can play chess? Can one of you tell me?
Visualization.
Visualization, how will they play chess verbally without a chess board?
They just say the notation and they memorize. They can
What-
remember all the moves.
So
And
what is the notation?
A1 F4.
A to
A1
H.
up to, yeah.
A to H and 1 to H.
Yes. So, I can say, I do king, this thing, whatever is their standard notation, and the other person can imagine the whole thing and reply. Now, as soon as you learn chess, can you do this?
No.
no.
You need years of practice and you need full dedication to chess. Maybe you're only interested in chess when you become such, when you become that comfortable in playing chess like that. This is something similar. When you do enough and when you develop some maturity in mathematics, you will see that proofs can be written down in plain English. I mean, very minimal notation will be required. They also needed A1, B2, etc. No, so in fact, the proof that I wrote down in n by n is easier than the proof that I wrote down for 2 by 2. Why? Because 2 by 2 we were starting. I could not have done like this. I should have done it in a bit more detail, which I did. But now that you have understood 2 by 2 very well, conceptually, we can explain n by n. So we have proved this. And this is enough for Abel's identity, right? This is enough for Abel's identity because W is a function, and now you're considering this as a function of X. So it is the same differential equation that you solved. So Abel's identity is done. So thus for solutions of linear homogeneous DE in standard form, I'm also assuming coefficients are continuous, though integrable may be enough for Abel's identity. Integrability of P1 is enough, maybe, but let's assume continuous, okay? Whenever we don't say it, is assume that all the function coefficients are continuous. The Wronskian is either never zero or
always zero.
Always zero. Why? Proof is Abel's identity because this is never zero. This part is never zero. E power something is never zero. So if it is vanishing at one point, then it vanishes everywhere. If it does not vanish at one point, then it does not vanish anywhere. This follows from Abel's identity. Okay, very good, excellent. So to continue, so we have done now the last part about linear dependence. We can do similarly, whatever we have done earlier. If y1, y2, so this we have done, and if y1, etc., yn, not necessarily solutions of ODE. This I am doing the first part. If two functions are linearly dependent, then the Wronskian is identically zero. That linear algebra I am doing first. Then we will come to differential equations. So if y1, etc., yn, not necessarily solutions of a differential equations. If these are linearly dependent, then what can you say? There exists coefficients C1, etc., Cn such that C1, y1 plus etc., Cn, yn will be zero. And what is the most important property of the coefficient C1, etc., Cn?
Not all
are
zero.
not zero.
Not all zero. Not all zero, such that this is zero throughout your interval of definition. Wherever you are considering your functions, throughout there, this is zero. Now you can differentiate this function many times. You will differentiate it n-1 many times and you will get the corresponding things. And if you put all this in matrix notation, what will you get? You will get the Wronskian matrix times the coefficient matrix C1, etc., Cn, the column matrix, equal to the zero matrix. And because it has a non-trivial solution, what can you conclude? The Wronskian matrices not invertible, right? If you have a homogeneous system of linear equations with a non-trivial solution, what is the conclusion about the matrix? Matrices?
Not invertible.
Not invertible. Because if the matrix was invertible, by multiplying by the inverse, you would have got trivial solution. So if non-trivial solution is there, matrix is not invertible in terms of the determinant is zero. Determinant is what is called the Wronskian. So this implies Wronskian is zero. So this is linear algebra. This is 106. There's no differential equations here. On the other hand, suppose y1, y2, etc. are also solutions of an ODE in standard form with continuous coefficients in your interval I. I'm taking open interval because I'm differentiating. Okay, that is not an important point. It is just the convention. Such that Wronskian is zero at some point is given. What will you do now? You will do exactly what you have done earlier. Because Wronskian is zero at one point, you will get non-zero tuple C1, etc., Cn, such that C1, y1, ith derivative, etc., Cn, yn, ith derivative is zero. Why do you get this? Because once again, at some point, Wronskian is given to be zero. And these are solutions. So all these solutions and their derivatives you consider at the point x0. You can form a homogeneous system, and that homogeneous system will have a non-trivial solution because Wronskian is given to be 0 at some point. Okay, so this is actually a homogeneous system of linear equations as in your linear algebra, and the corresponding matrix, the determinant is 0 is given, and therefore you will get a non-zero solution. Okay, so this is linear algebra. Now you consider this function c1y1 plus etc plus cnyn. This function is considered throughout I. Throughout I. And what will you conclude about this function? What will you conclude about this function c1y1 plus etc cnyn?
It is also a solution.
It is, of course, it's a solution, and this solution is
0 throughout.
What is my claim? If y1 etc are solutions of ODE, and if Wronskian is 0 at one point, what should be my claim? What is the claim from the title? Y1 etc yn are linearly
Dependent.
dependent because Wronskian is 0. So what should be my claim here? This function is c1 etc cn is non-zero, and this function is identically zero where on
I.
And can you finish the proof is what I am asking. Can you say that this function is identically zero on I? Can you conclude the proof?
Using uniqueness and
By
existence.
uniqueness.
Which two functions are you going to consider?
The f and the identically zero function.
Yeah. And what is your IVP?
Each row of the Wronskian at x0.
Given differential equation together with
Each row of the Wronskian at x0.
y at x0 is 0, y prime at x0 is 0, etc. y n minus first derivative at x0 is 0. Okay. So the constant function 0 clearly satisfies that, but does f satisfy that IVP?
Yes.
Yes, because f anyway satisfies the differential equation because y1 etc yn are solutions of the differential equation and it is homogeneous. So f will satisfy the differential equation. And does is f at x0 0?
Yes.
Yes, because this is true for all I. So f at x0 is 0, f prime at x0 is 0, etc. f n minus first derivative at x0 is 0. So this given function f is a solution to the IVP that you have constructed in your mind. I have not written it down. Okay, and constant function 0 is also obviously a solution of the same IVP. But an IVP cannot have two solutions. Therefore, f has to be identically 0. And if f is identically 0, you have got non-zero coefficients so that the linear combination is identically 0. Meaning y1 etc yn are linearly dependent, and because of this condition, Wronskian is 0 at one point, you have concluded that from the fact that Wronskian is 0 at one point, you have concluded that the functions are linearly dependent. Do you think that this is exactly the same proof that I have done for n equal to 2 or slightly written differently? Was this exactly the same? Idea is the same, but line by line, is this exactly the same proof that I have done earlier? There's a slight difference. Earlier, when I had only f and g, I said one of them you can assume not identically 0, and therefore it is non-zero at a point, and therefore by continuity it is non-zero in some subinterval, and then there I considered the function g by f, and I considered its derivative. Okay, I used that, but I could have done it like this also. In fact, this is better because this generalizes to n very nicely. You agree? There's a slight difference. There I said g equal to a constant times f instead of saying af plus bg is 0. See, when there are only two vectors, a linear combination of 0 is same as saying one is a multiple of the other. But when there are n vectors, you cannot say like that. You have to say a linear combination is 0. You agree? Say something, otherwise I don't know whether you are there or not. I can't see any of you.
Yes, sir. Yes, sir.
Okay, so I have written the proof slightly differently so that the proof for n is easy to write. And this is anyway a better proof. So why didn't I do it at that time? I wanted to give, I want to show some difference between 2 and n in argument. This proof also works for n equal to 2. So consider this function and g identically 0 and apply uniqueness theorem to conclude that these are linearly dependent. Okay, what is the IVP here? The given differential equation together with y at x0 is 0, y prime at x0 is 0, y n minus first derivative at x0 is 0. Okay, now let us stop here. It is time. So what am I going to do in the next lecture? I will start here, constant differential operators. If all the coefficients are constant, can you make a quick guess and then we will stop? Suppose you have constant coefficients. Will you get an option? Yeah, you will. Suppose you have a third order differential equation with constant coefficients. You will get a characteristic polynomial of which degree? 3. And suppose you have 3 distinct roots. For that characteristic polynomial, assume you have 3 distinct roots. Can you write down the general solution? Suppose M1, M2, M3 are the distinct roots.
Yes, sir.
E power M1,
E power M1x, E power M2x, E power M3x. Very good. Suppose you have 2 distinct roots and 1 more root. Suppose your roots are 2, 2, 3. 2 is repeating twice and 3 is coming once. Can you write down the general solution?
C1 plus C2x e power.
Give me a basis. Give me the obvious basis. No need to say C1, C2, etc. Suppose 2 is coming twice. 2, 2, 3 are the roots. What should be?
E power 2x, x e power 2x, e power 3x.
Very good. Excellent. Suppose the roots are 1000, 1000, 1000. What's the basis?
X e power 1000x, x square e power 1000x, and e power 1000x.
Very good. So if 1000 is coming 3 times, the answer is e power 1000x, x e power 1000x, x square e power 1000x. Now suppose you get the answer to be 1 plus I and 2, and can you guess the third root? If one root is 2 and one root is 1 plus I, can you guess the third root?
1 minus
1 minus I.
Because
complex conjugate.
Complex roots will come in pairs. So suppose the roots are 2 and 1 plus I and 1 minus I. Can you guess the basis? 2 tells you what is an answer?
E power 2x.
E power 2x, and 1 plus I and 1 minus I together will give you basis what?
E power x
E power x cos x, E power x sin.
E power x sin x and E power x cos x. Wonderful. So my next lecture is done. All of you have finished the theory. Okay. So what will we do in the next lecture? Whatever you have guessed, we will theoretically prove that all your guesses are correct. Okay. So that's what we will do next time. Can I go a bit faster in the next lecture? Because anyway, you know the answers, right? What you have done for 3, also yes, you can do for n, no? You have got the pattern, right?
Yes, sir.
Yes. So what we will do is we will give a quick proof of whatever you have guessed very correctly, very nicely. I'm very happy. As a teacher, nothing is more satisfying than students predicting what is going to come in the next lecture. That means you have developed enough intuition and you have understood whatever I have covered very well. Okay, excellent. So that also means in the next lecture, I can go a bit faster because you have already, developed the intuition. You have guessed everything correctly. So excellent. Congratulations. Let us stop here. And as I told you in the very first slide, what did I tell you in the very first slide about today afternoon?
No interactive
session. Very good. Excellent. So nobody will wait for me and we will meet on Monday. Have a good weekend. So see you on Monday. Shall I end the meeting or okay, let me stop sharing and let me stop recording. If you have any quick question, we can discuss. And after that, I will end the meeting. Let me stop the recording anyway.
Sorry.